Okay, so now we're ready to appreciate something more sophisticated, right? You've got the idea of cyclohexanes and how to draw them. We talked in our last video about what it means to have an axial position or an equatorial position. This is a little difficult for people's eyes sometimes. Do appreciate. Can you see that this carbon is above the six-membered ring and that carbon is below it? Can you see pointing down? Can you see a pointing up arrow right here and a pointing down arrow right here? So the ones that are pointing up are going to have an axial position that goes up, right? So there's another axial position here. In this case, it's just a hydrogen because we don't have anything drawn there. This one is going to be going down. Those are all the axial positions. There's one going down. Here's one going up. Here's one going down. 1, 2, 3, 4, 5, 6. Those are all of them, okay? Now, after we get a ring flip, though, this thing is flopping back and forth. Don't forget bonds always turn with, or try to turn with respect to each other, right? So you might get a ring flip where the axial, what was the axial position is now in the equatorial position, right? So ring flipping occurs by rotation of the carbon-carbon bonds in the ring, which is what we would expect, I guess, if you're used to bonds. And so you can go from the axial position to the equatorial position and back, all right? And actually things do go between the two, between the axial and the equatorial position. All right, so, and by the way, let me go back. This is not a resonance anymore. Let me point out, this really is an equilibrium, right? So notice we use a different arrow for this than we do for resonance, right? It's a back and forth because the real thing is not a blend between the two. Each molecule has an X either in the axial position or the equatorial position. Let me go back a couple slides here. Remember this? Remember this picture? So it turns out this would be like an equilibrium, right? Where the axial, where you have your ring flip is going to go through different things like that, right? So it's definitely some energy. You've got, in order to go from here to here, we got to overcome a couple energy barriers with activation energies, right? I've seen stuff like that before. But, all right, so that's what we're talking about with respect to ring flips. Now, let's consider that what I had its X in the previous slide is now a methyl group. If we have a methyl group here in the axial position, or it goes to a ring flip into the equatorial position, we find that 95% of it is really over here because the equatorial position is the more stable chair. All right, if you've got something in that equatorial position at room temperature, 95% of the methyl cyclohexane molecules, 95% of them are going to be in the equatorial position. Okay. All right, the axial position finally is more energetic, is higher energy because of steric interactions. So let's look at that. So you've seen this before. We used Newman projection before. Remember this, the gauche interaction, right? So if we're looking down that bond, if this is carbon 1 and that's carbon 2, we're looking down the 1,2 bond. And on the carbon 2, there's a methyl group. On carbon 1, there's a methyl group. And these guys are 60 degrees with respect to each other. They're staggered, but they're gauche, right? They're not anti. Can you see how they're closer to each other than they might be? So that gauche interaction is what causes the steric strain when the methyl group is in the axial position, right? There's another carbon over here, and that is gauche. Can you see that? Like there's 60 degrees right there. And it's called a 1,3 diaxial interaction. It's really just that gauche interaction. It's the same thing. All right, so here's a picture with sort of, you might imagine, the big electron cloud around it, and those electron clouds are all repelling each other. So the 1,3 diaxial, I just said that. The 1,3 diaxial interaction is actually a gauche interaction. All right, so let's compare different substituents. If we have chlorine in the difference between axial and gauche is 2 kilojoules per mole, okay? So that 1,3 diaxial interaction for chlorine is 2. If we have a hydroxy, and I pulled one up here, let's look at this. Can you see what I've got here? So I've got a cyclohexane, okay? Got a cyclohexane. That is a chlorine. I'll put a chlorine in the equatorial position. Can you see that? But let's put it into the axial position. Let's go hydrogen. Boom. Let's make that chlorine. I'm working on Avogadro right now. I use these different tools because that's a fluorine. Let's do chlorine. Okay, now there's a chlorine in the, can you see it's getting pushed away? So I've got it, watch this, stop. Can you see that? I've got it in an optimization mode here. I'm using a force field of Merck Molecular Force Field 94, MMFF 94. And so watch this, start that. Let's go back here. Go back here, make that a hydrogen. Watch what happens. No, not a boron, a hydrogen. No, okay, just a second here. Won't delete. Won't delete, okay. So watch this now. So I'll turn this guy around. It's in an optimization stage right now, so I've got a little tool on here. Stop. Okay, let's start it again. And let's take that molecule and make it back to a chlorine. And we'll put the chlorine in the axial position, click. And you see how I get pushed out like that? That's pretty cool. All right, so you can't perhaps see that, but that's higher energy because it's in the axial position. All right. All right, I hope those pictures are helpful to you. So if chlorine's in the axial position, there's a difference of 2 kilojoules per mole, and the ratio is 70 to 30. If hydroxy is in the axial position, let's do hydroxy, it's cool. Well, oxygen, watch this. Make that an oxygen, that's a hydroxy right there, right? That's in the axial position, and that, I think we could get that guy turned around, that would work better, wouldn't it? I wonder if I can grab that and move it. Yeah, I can. Look at that. See that? I just grabbed it and moved it around. Seemed like it'd be better if it was out than if it were in, right? Okay. So there's a hydroxyl. I removed the balls for the atoms, and I'm just having sticks now, okay? So that's an oxygen atom. There's a hydrogen and a carbon. All right. So let's go back here. If an oxygen is in the axial position, it's 4.2 kilojoules per mole. Makes the ratio 83 to 17. If there's a methyl, it's 7.6. Makes the ratio 95% axial, or no, equatorial. If it's ethyl, it's 96% equatorial. If it's isopropyl, it's 97%. And if it's tert-butyl, it's 1,000 to 1. Wow. Okay, so we've been introduced now to cyclohexanes, how to draw them. We've considered monosubstituted cyclohexanes. I bet you can guess what's next.